from the studios of Postscript Media and Canary Media.
I'm Shayle Kann, and this is Catalyst. How big exactly is the average Portland cement plant right now? Like, give me a sense of scale.
They are colossal. So the average small Portland cement plant produces 1 million tons of cement per year. And, on average, 1 ton of cement, just rounding up to big numbers, 1 ton of cement produces 1 ton of CO2.
It's time to cement your understanding with concrete ideas about how to decarbonize the built environment. Please forgive me.
Catalyst is brought to you by CohnReznick Capital, a leading renewable energy investment bank servicing the U.S. sustainability sector. With the passage of the IRA and the global shift towards greater ESG investing, expert financial advisory services are more crucial than ever. Learn more about how CohnReznick Capital can help with your project finance and M&A needs by visiting CohnReznickCapital.com.
Mark your calendar for November 30th at 1 p.m. Eastern. That is when we are hosting a live episode of Climavores. It's remote, it's on Zoom, and co-hosts Tamar Haspel and Mike Grunwald will be talking with renowned author and NYU professor Marion Nestle about food history, nutrition, eating for the planet, and who you should and shouldn't trust on food. And we're taking your questions too, so pop into the show notes, click the link, and come join Climavores live on November 30th. Hope to see you there.
Catalyst is supported by Scale Microgrid Solutions, your comprehensive source for all distributed energy financing. Backed by Warburg Pincus, Scale gives developers more certainty and simplicity in the financing process. They're investing hundreds of millions of dollars into solar, energy storage, microgrids, EV infrastructure, CHP, and more. Their unique technical expertise allows them to pull projects over the line, no matter where they are in the development process. Distributed generation can be complex. Scale makes financing it easy. Visit scalecapitalsolutions.com to learn more.
I'm Shayle Kann. I'm a partner at the venture capital firm Energy Impact Partners. Welcome. Now, normally I jump straight from that into today's topic, but actually I do want to spend just a minute this time talking about my day job, which is what I spend 120% of my time on, and then whatever's left after that goes to sitting behind a microphone talking to you all. It's a big week for me. We just announced this week that we at EIP had done the final close on what we call our Frontier Fund, which is what I've been working on for the past couple of years. It's a $485 million venture capital fund dedicated to investing in revolutionary technologies to enable deep decarbonization. So the idea here being we've got 50 gigatons, 50 billion tons of annual emissions of CO2 equivalent in the world. We're going to have to take that from 50 billion down to net zero by mid-century or earlier. In order to do that, we're going to have to fundamentally transform numerous industries whose total addressable markets measure in the trillions. This is an enormous challenge, and it's going to require some really big swings with really fundamental technology advances to get there in time. That's what we're looking to invest in. Those are the entrepreneurs that we're trying to partner with. And we've been at it for a couple of years and love the dozen or so portfolio companies we've already got, but we've got a lot more work to do. So if you're an entrepreneur who's leveraging some fundamental technology advancement to help us get from 50 billion to zero, then please get in touch. And in the meantime, on to today's show. So here's the main thing you need to understand about cement and concrete. We collectively, humans, produce a truly ridiculous amount of it. Cement is, in fact, the second most consumed material in the world, second only to water. We use around 30 billion tons of concrete every year. And its consumption has been growing. We actually use 3 times as much per capita today as we did 40 years ago. But we've been making it a very long time, literally for millennia, back to ancient Egypt. But alas, the emissions. It's responsible for something on the order of 6 to 8% of global greenhouse gas emissions, right up with steel for the largest source of industrial emissions in the world. Big problem, obviously. And a bunch of different pathways toward partial or complete solutions in some cases. It's a complex value chain with multiple causes of emissions. So perfect for us to discuss. My personal favorite entrepreneur and cement decarbonizer is Leah Ellis, the co-founder and CEO of Sublime Systems, which is an incredibly exciting early-stage company tackling the heart of the cement decarbonization problem. I'm biased because we at EIP are investors in Sublime, but I suspect you will find yourself biased once you hear from Leah as well. Here she is. Leah, welcome.
Thanks, Shayle. Pleasure to be here.
Excited to talk cement and concrete with you. We're going to start with some basics, and then, as usual, we're going to get into some wonky details. But let's start at the highest level. First of all, because I've heard a lot of people confuse these two things. What is cement and what is concrete?
So cement is the glue that holds concrete together. So concrete is cement, sand, aggregate, and water mixed together to hold everything in place. So cement is essentially rock glue. So if you think of paper mache with paper and glue, so cement is that glue that holds the final form.
And cement is kind of like the core building block of concrete, right? Is that the right way to think about it? Like, people talk about how much concrete we use as a society globally, and it's a ridiculously enormous amount. But in the production process of that concrete, most of the industrial part of it is the cement production. Do you think of it that way?
Well, concrete is about 90% rocks and 10% cement. But even so, cement is the most massively produced man-made material in the world and second most consumed material besides water. So even if it's just 10% of concrete, it's still produced in tremendous volumes.
Just speaks to how much concrete we use. If cement is only 10%, it's still the most produced thing second most produced thing in the world. All right, let's talk through the production process. So just walk me through kind of end to end today in the standard cement and concrete production process. What do we start with and how do we get to concrete at the end?
Yeah, so cement is essentially a calcium silicate. So the way we make cement today, it's made in a long rotary kiln. So it's a big kiln that rotates at a 5-degree angle. So you put rocks on one end, and as the kiln rotates and spins, the rocks sort of tumble towards the end of the kiln, which is very, very hot. And you get two chemical reactions, basically two chemical reactions happening as the rocks fall down this kiln and get made into cement. The first reaction is the conversion of limestone, calcium carbonate, into calcium oxide. So calcium carbonate, the major component of cement, is it's chemically inert. So calcium bound to CO2 can't react with anything. And then at around 1,000 degrees Celsius, so about halfway down the kiln, the calcium carbonate breaks up into CO2, which escapes as a gas, and calcium oxide, which then goes on in a second step to react with the silicates to make Portland cement, which is the cement we largely use today.
So we'll come back to where the emissions come from in that process in a minute. But I thought it would be interesting to talk a little bit about the history here. As you said, Portland cement or ordinary Portland cement is, I think most folks will know, like pretty ubiquitous. It's most of what we use today. It's not the only cement that is out there. There are others. But how did we end up where we are today, where Portland cement is so widely adopted? Is it just the best cement in the world, or is it some kind of relic of history?
Yeah, there are many types of rock glue that we've been using over the past millennia as humans. And it all started, thousands of years ago when people would burn limestone to make lime, the calcium oxide, and then use that as a mortar for brick making or for building pyramids and ancient structures. So that was, the first type of construction material was a lime clay mixture. And then the Romans, of course, pioneered a new type of cement. So they started using volcanic ash, and they were blessed with large quantities of volcanic ash thanks to their geography, and that has turned out to be quite a fantastic cement. So their cement was, one part burnt limestone, lime, and one part volcanic ash, and it's proved to be incredibly durable. So, the Romans came and went, and then, following the Romans, cement was still made by burning limestone and mixing it with clay. And then what happened about 200 years ago is someone discovered, almost quite by accident, that if you had a specific chemistry of rock, so if you had the right calcium to silica ratio in your input limestone that you were burning, and you heated it to an extra hot temperature, so around 1500 degrees Celsius, you got what's now known as Portland cement. So Portland cement contains a very special phase called tricalcium silicate, which is only stable at around 1500 degrees Celsius. So as it falls out of the kiln and is quenched, this tricalcium silicate phase is sort of frozen. And that phase is what leads to Portland cement's very high early strength and early set time, which has allowed us to, build vertically, and build very quickly. So that's been the evolution of cement over the past few thousand years.
Good brief history of cement. You mentioned early strength and early set time. This is another thing I wanted to talk through with you. So different formulations of rock glue have different characteristics. And I'm interested to hear sort of like, what are the ones that you think of as, or maybe not you, what are the ones that architects and designers and engineers think of as being the most important? Like if you're going to have a good quality cement, what are the things that you absolutely need to achieve?
Yeah, of course, all the properties are important, but the main ones are compressive strength. So you want it to be strong. So cement is very strong in compressive strength, not so good in tensile strength. So you need about 30 megapascals after 30 days. There's also early age strength and quick set time. So set time is a little bit different from early strength in that you want your cement to gel and harden. And this means that the contractor can go home, and doesn't have to stand around a long shift shooing kids off from, writing their names in wet concrete. So what's interesting is that 90% of the total installed cost of concrete is actually labor from the contractor. It's often unionized labor. And cement, being a commodity material, is so cheap. So Portland cement is around $130 a ton. So basically the most important properties are the ones that minimize labor costs. So having that early strength, early set time, proper flow out of the truck so that it doesn't require too much water. And then of course, durability. So you don't want to have cracking or corrosion or expansive reactions with, different minerals in the soils. And so that's very important too.
Okay, so back to Portland cement then. So as you said, we discovered it a couple hundred years ago, and it turns out to have these attractive characteristics on early strength and set time. Is it the high watermark? Is it the highest performing cement? Or I guess the other way to ask it is just, why is it that Portland cement is so ubiquitous?
Yeah, I guess it's ubiquitous because it works, and it's been sort of a one-size-fits-all cement for a very long time. And of course, there are cements that have, faster strength, set times and faster early strengths. And so those are used for, let's say, patching up highways in the middle of the night so that everyone can drive on them. But, for a long time, it's overshot the technical requirements for certain applications. So, there's thousands of different things that we use cement for, and not all of them require the properties that Portland cement brings.
All right, so let's talk through the value chain then. Like who is doing what today in this massive cement and concrete industry?
Yeah, it all starts at the Portland cement kiln. So Portland cement companies are often very large international companies. So there's a handful of colossal companies that own the majority of the Portland cement kilns all around the world. So they're often located near a limestone quarry because cement's very bulky. And of course, half the weight of the limestone gets lost to CO2. So they're located next to a quarry, operate these big kilns, and then ship the final cement powder by train or by boat to a port, and then that's used by ready mix concrete. So in every city and in every town, there's a ready mix concrete producer. Some of them are vertically integrated with these large cement companies, and some of them are mom and pop or family operations or independent companies, and they operate these spinning trucks that we see, and they sell to contractors who are told what to buy from a structural engineer who's specified, a certain cement for a certain purpose, all designed by an architect. And then, of course, ultimately everything is paid for by the building owner. So there's quite a long chain of value all throughout.
So the way I think about it, you could tell me if this is right, is that cement production, Portland cement production is highly centralized. Those plants, as you said, they're near limestone quarries because you don't want to ship limestone around. As you said, you're going to lose half the weight when you turn it into lime anyway. So that's very centralized, and those plants are big. And then what we ship around is the cement powder, and then you get to the ready-mix concrete world, and that's actually fairly distributed. Not down to the level of necessarily the individual construction project, but down to sort of the local, regional level.
Yeah, exactly. So about 80% of ready-mix plants are independently owned.
How big exactly is the average Portland cement plant right now? Like, give me a sense of scale.
They are colossal. So the average small Portland cement plant produces 1 million tons of cement per year. And they go all the way up to 3 or 4, maybe even 5 million tons of cement produced per year. So absolutely huge. And, on average, 1 ton of cement, just rounding up to big numbers, 1 ton of cement produces 1 ton of CO2.
Okay, that's a great segue into the next thing. So one thing I think people, everybody who's looked at cement understands this, but otherwise people don't necessarily recognize that's a little bit different about cement production versus other sources of large industrial emissions, is that you've got 2 separate, very big components of emissions. This is part of why cement production is such a huge overall number on emissions. So walk me through where the emissions come from in the cement making process.
Yeah. Cement being the most massive industry by volume in the world also produces an almost equivalent amount of CO2. And that's, again, speaking in big even numbers, it's roughly half from the fossil fuel needed to get to 1,000 degrees and 1,500 degrees to decompose the calcium and have it fuse with the silicates. And the other half of the CO2 is from the limestone itself as it decomposes into the oxide. And this is what makes cement one of the most difficult things to decarbonize from a technical standpoint, is that you need limestone, so you need the calcium oxide, and then you also need to get to these high temperatures to make the calcium and to make the silicate. So there's almost no way around that except for post-combustion carbon capture if you're making Portland cement.
Right. So we'll come back to the ways to potentially decarbonize, but yeah, to repeat that point. So you've got one challenge, which is you need to heat a kiln really, really, really hot. Industrial heat is a big challenge across a variety of industries. And this is one that is among the hottest, 1,000 or 1,500 degrees C, that we've done historically by combusting fossil fuels, basically. So that's, a big chunk of the emissions there. And then the other one is in the actual chemical reaction that naturally and unavoidably, if you're turning limestone into lime, the byproduct of that is CO2. And there is no alternative going from limestone to lime then to produce CO2. Now, what you do with that CO2 is a different question, but that is like a natural part of how we produce Portland cement, at least, and makes it a particular challenge because you could solve the industrial heat problem, you haven't solved the process emissions problem. You could solve the process emissions problem, you haven't solved the industrial heat problem. So if we're seriously going to try to decarbonize, we have to figure out a way to deal with both of those things, right?
Exactly. You put it very well.
All right, so let's talk about decarbonizing then. There's, one of the things that's interesting about cement, in part because it has this multi-stage value chain that involves cement production and involves turning that cement into concrete, there have been a bunch of different ideas proposed for how we can decarbonize part or all of this market. Let's run through a few of them, and then I think we'll spend a bunch of time talking about Sublime's approach, obviously. But at the high level, what do you think of as the major categories of decarbonization possibilities?
Yeah, the major categories are post-combustion carbon capture. So you'll see this in all of the major cement companies, their pathways to net zero by 2050. You'll also see alternative fuels, so burning things other than fossil fuel, be that tires or biomass. You'll also see big cement companies using supplementary cementitious materials. So like I said before, Portland cement has been used, especially in the US, as a one-size-fits-all cement. But there are a number of things that you can blend into cement that actually improve the performance and durability. And so you can tailor the percent of Portland cement you use for each application. And this is done increasingly in Europe, where the cement is blended to meet specific, performance or CO2 goals.
Can we talk about that one for a minute? I think post-combustion carbon capture is fairly straightforward, right? Everybody understands what carbon capture is. You have a cement plant, you capture the CO2, you do something with the CO2. We can talk about why there are challenges there, but that one's fairly straightforward. The second one you mentioned, maybe a little bit less obvious, but right, alternative ways to heat the kiln, basically, of which there are a number, and could decarbonize that portion of the emissions, but don't do anything about the process emissions. That third one, supplementary cementitious materials, I feel like that one actually is, at least for outsiders, like a little more complicated to understand. So like, what are these SCMs and how much can you blend in, and how big a difference does that make on the total life cycle emissions of cement if you are just using a little bit less Portland cement?
Yeah, that's a fantastic question. So what you're normally blending into Portland cement are silicates. So Portland cement, as I said before, is a tricalcium silicate, which means there's 3 calciums for 1 silicate. But the hardened form of Portland cement is, the phase that gives it its strength is one calcium to 1 silicate to 1 water. So it's called CSH with a stoichiometry of approximately 1 to 1 to 1. So when you hydrate Portland cement and add water to it, you have a lot more calcium floating around than you really need. And this, doesn't do you any favors for a strength and durability standpoint. So folks add extra silicates to the cement, and that soaks up the extra calcium, and that improves the durability, improves the density, and also improves the performance in many ways. So there are a number of different sources of silicates. Right now, fly ash is very popular. So fly ash is an amorphous silicate collected from coal-fired power plants. And of course, those are going away, and for a good reason. But it does mean that there's a shortage of fly ash, a near-term shortage. And, we're also increasingly using fly ash for sustainability reasons, although you could argue that perhaps it truly isn't a sustainable product since it has quite a bit of embodied carbon in it, depending on how you allocate that to the electrons or to the fly ash. So there's a number of different silicates, so natural silicates, clays, pumices, obsidians, and different materials coming to market to replace fly ash.
And how big of a difference can adding SCMs make on emissions and, I guess, on cost?
Yeah, so you're right. Another reason why they're added is because of cost. They're oftentimes less expensive than Portland cement. And so these SCM, supplementary cementitious materials, have been used for decades before cement came into the spotlight as something that had a big CO2 footprint. And that's because they, reduce cost. So you're blending in something that's much less expensive. But you can only blend in so much before you start you're blending it in to remove some of that extra calcium. But if you add too much silicates, now you have too much silicates. And so it's that reaction between the calcium and the silica that make the hardened cement. So you can only blend about 30% in before you start reducing, diluting the performance.
Right. So in other words, you can have a meaningful but incremental impact. You can maybe lower cost, you can maybe increase strength. So it may be like the right thing to do in a lot of cases. From an emissions standpoint, there's no world in which that totally decarbonizes cement because you still need 70% Portland cement. So if you don't solve for the Portland cement production process, at best you're getting a 30% emissions reduction.
Exactly. So, going back to where the CO2 emissions from cement occur, a lot of it is in that decomposition of calcium. It's producing the reactive calcium. And so you really need need to have both calcium and silicate in the cement. So you can't totally decarbonize just from that silicate angle.
Support for Catalyst comes from CohnReznick Capital, whose experts have been driven by their passion for ESG and sustainability since day one. Whether helping solar and storage developers raise capital, optimizing structures for carbon capture projects, or helping investors navigate their way through the ever-evolving sustainability sector, CohnReznick Capital stands ready to help clients power forward.
What are you doing on November 30th at 1 p.m. Eastern? I hope you'll be with us for a virtual live episode of Climavores, our show on food and climate. We are going to be featuring author and NYU professor Marion Nestle. Marion has been a towering and trusted figure in nutrition science. She joins Climavores co-hosts Mike Grunwald and Tamar Haspel, who will grill her about food history, food politics, food justice, and how to eat for a healthy body and healthy planet, plus who to trust on nutrition. I'm going to be moderating that event, and I hope you'll come for a lively virtual discussion on November 30th at 1 p.m. Eastern. You will be able to ask questions as well. Learn more and RSVP at the link in our show notes.
Scale Microgrid Solutions does a lot more than build industry-leading microgrids. Combined with their technical expertise, Scale finances and acquires distributed energy projects of all sizes. Backed by Warburg Pincus, Scale takes an integrated approach to distributed energy financing, setting up developers for success by creating more certainty and simplicity in the financing process. At Scale, the engineers, designers, lawyers, accountants, and project finance experts all work under the same roof, which cuts out intermediaries that add complexity, risks, and costs for developers. Distributed generation can be complex. Scale makes financing it easy. Visit scalecapitalsolutions.com to learn more.
Okay, so we've talked through three of the categories. The fourth, I think that's at least worth mentioning, is on the concrete side more so than the cement side, which is, injecting CO2 into the curing process and using cement as basically a sink for captured CO2. How do you think about that fitting into the broader cement decarbonization picture? Or I guess concrete decarbonization picture?
If I may, before going into CO2 injection, I'd like to add in a fun fact about alternative fuels. And that is that cement kilns, because they run at such an absurdly hot temperature, they actually form a pretty important part of the garbage ecosystem. So you can burn a lot of waste that you couldn't end up getting rid of another way. So medical waste, tar paper, unrecyclable plastics, even cement kilns around the world use camel dung in Saudi Arabia. So I think it's actually quite cool that, there's a use for these, there's a garbage ecosystem that cement can sort of take any type of undesirable carbonaceous waste, and at that obscene temperature of 1500 degrees, almost everything vaporizes into CO2 very quickly at that temperature. So I think we've all seen tire fires, and of course they produce a black choking smoke. But when you throw a tire into a cement kiln, at that temperature, it just vaporizes entirely into CO2 within a matter of seconds. So it's actually a pretty clean way of getting rid of some pretty dirty materials. So I think there's a pretty cool role for cement kilns in the circular economy.
Good aside.
Going back to CO2 injection, yeah. So you have calcium oxide in the cement, and you can add CO2 back and have it convert back into limestone, that calcium carbonate. So that goes back to one of the earliest forms of cement that I mentioned, just using burnt lime and then, using it as a mortar, and then it reabsorbs CO2 from the atmosphere as it hardens. So there are a number of startups looking to use this type of technology for making precast blocks. So, having the lime and then, putting it in an autoclave, pressurizing it and forming CO2 cured rocks, which is great. And then we have carbon cure, which adds a small amount of CO2 into the ready mix concrete, so the cast in place concrete, and that even though they're adding just a small amount of CO2, it is said to improve the strength so that you can end up using less cement overall. So, this is a pretty cool technology, but it is somewhat limited because CO2, as we know, is an acid. So it lowers the pH of concrete when you fully mineralize the cement. So that causes rebar corrosion. So the rebar, the steel inside this structurally reinforced concrete, is passivated from corrosion by the alkalinity of the cement. And so when that cement acidifies through carbonation, you start getting rebar corrosion. And that's where cement cracks and starts to fall apart and you have durability concerns. So that's why these CO2 injection startups are mostly limited to precast applications where you're not using rebar. It's actually interesting, another small tangent about cement. So Portland cement does recarbonate over time. So if you have like a piece of pavement, for example, it will continue to absorb CO2 from the atmosphere over timescales of, decades to 100 years or millennia, will totally turn back into calcium carbonate. So it is a CO2 sink, which is a good thing. However, the fact that cement absorbs CO2 is also a degradation reaction. So it's kind of a double-edged sword. So it's constantly absorbing CO2, but then at a certain point, it all falls down. So that's why structural engineers will often bury their rebar. They'll use even more cement than they have to for structural purposes to bury the cement so far into the building so that as the carbonation front increases and, as the building starts absorbing CO2 from the surface, that rebar is so far into the structure that it's protected for a very long time.
That's fascinating. I did not know that. Is it enough of a CO2 sink to matter from a, global CO2 flux perspective? I mean, we have a ton of cement out there.
Yeah. So, I think it does matter. However, it will only absorb the limestone emissions. So it'll only absorb about half of its original CO2 footprint.
Right. And over decades to centuries, which we don't necessarily have that much time. It's just interesting that we think of what are the major global CO2 natural sinks that are just out there sucking up CO2, things like trees and plants and all of that. And it's funny to think about cement being one of those.
Yeah, totally. And so a big factor in that is the surface area to volume ratio of the cement. So if you have an old building, crushing it up into finer particles will really accelerate the carbonation.
Fascinating. Okay, so now we come around to Sublime, which you're doing none of the things that we've described so far, right? All these different pathways, which are all interesting to partially decarbonize cement production. Sublime's taking a totally different approach. So what are you working on at Sublime? And then we'll get into why.
Yeah. So Sublime is pioneering a new way to make cement. So we use electricity instead of fossil fuel to drive the decomposition of calcium-bearing minerals into a cement. So my background is in electrochemistry, worked previously on batteries, as did my co-founder. So we were looking for a way to use our electrochemical toolbox. So working at ambient temperatures, working with intermittent electricity, and we were trying to find a way that we could use electrochemistry to displace the fossil fuel in the process.
Okay, so part one of what Sublime is doing that's novel is you're replacing the kiln, which is the thing that you have to normally heat up to 1,000 to 1,500 degrees C, with an electrochemical reaction that occurs at room temperature. How do you think about the benefits of that relative to the traditional kiln?
Yeah, so the benefit is that it's lower in CO2. So obviously we're getting rid of that half of cement CO2 emission that's from the fossil fuel. And also we can get rid of the other half of cement CO2 emission, which is from the minerals or the limestone that's used. And what's cool about Sublime's process is that it's not a thermal decomposition of the calcium carbonate. So remember, calcium carbonate decomposes in a kiln and the CO2 escapes as a gas, and then you have a solid calcium oxide. So Sublime goes about this in a different way. So we take a source of calcium, It could be calcium carbonate. It could be something else. And then instead of thermally decomposing it, we put it through an electrochemical process that dissolves the calcium, so extracts the calcium as a liquid, and then precipitates it in a second step. So this means that we can use calcium carbonate, in which case, when the calcium is extracted, we're left with pure, cold, compressed CO2, so inherently captured CO2 that's ready to go into a pipeline or to be used in food-grade applications, a very low cost of capture, less than $10 a ton. Or we also have the option of using non-limestone minerals. So there's a long list of calcium-bearing minerals we could use, a number of natural minerals and waste materials, largely silicates. And so we can pull the calcium out of the silicate and then use both the calcium and the silicate in cement to make that calcium silicate hydrate.
So this is one of the things that's cool about Sublime. So you have kind of two different pathways to fully decarbonize cement production, right? So you've got the emissions from what would have been the emissions from the kiln solved by electrifying it. Now, obviously, you got to use low carbon or zero carbon electricity, but let's assume we do. That part's solved. Then there's the other part, right, which is the decomposition of the rock. And you're saying there's sort of two different things you could do there. You could use the traditional material, in which case you are doing a form of carbon capture, but it's not really apples to apples with post-combustion carbon capture. You're basically just as a natural part of your process, you're getting a pure stream of CO2 to which you don't need to do a whole lot. You just got to figure out where the home is for it. Or if you want to avoid that entirely, which is, I think, important to talk about because it is not the easiest thing in the world to do something with a huge stream of CO2, right? We're seeing this already in all these carbon capture projects. You have to have pipelines and you have to have permanent sequestration or a big sink or whatever. So, in the event that you don't want to or don't have a home for all that CO2, you're saying you can use different inputs, still run your electrochemical reaction, and then you don't get any CO2 out at all. But in that case, you're not producing Portland cement, right? So how do you think about this back to our original conversation around like how Portland cement ended up being so ubiquitous? How do you think about the future of cement types? And is there room in the market for something besides Portland cement to take a big role? And what would it take for that to happen?
Yeah, great question. So, we don't use a thermal process in the kiln. So, we don't have 1500 degrees Celsius, and therefore we don't make that tricalcium silicate phase that's only stable at that temperature. But we still make, in the end, that calcium silicate hydrate. So the final hardened phase of cement and all that durability and compressive strength associated with it are the same. But we go about it in a different way that's all at very, very low temperatures. And I think, the cement market being absolutely huge, and then also with so many performance requirements for these different applications, there's a lot of, the future of cement, and it's already happening even long before Sublime, is all about the performance you need for a given application. And this started, way back in the 60s, 70s, and 80s when slag and fly ash started getting blended into cement as a supplementary cementitious material, that people started rethinking the way that cement was specified. So previously it was all chemistry-based specifications. So your cement had to have a certain percentage of that tricalcium silicate phase. But now architects are moving towards performance-based standards. So there's standards for blended cement where it's 50% CO2, Portland cement, 50%, almost anything you want, as long as it meets this performance-based standard. And there's a bunch of tests to prove that. And there's also 100% performance-based standard where, structural engineers say, we don't care what it's made out of, just give us something that works.
And so the idea being, if those performance-based standards take hold more and more, then what dominates the market in the long term is not a particular formulation. It's not Portland cement or any other particular formulation. It is anything that has been, blessed as meeting those standards. And that's the pathway to a market where you never needed to use limestone in the first place to make cement.
Exactly. And I think that's really exciting because there's so much room for innovation when you're working with, trying to hit targets that, the customers and the end users actually need, which is a strong, durable, fast-setting cement. And you're not limited to just trying to achieve a certain chemistry that, is associated with these very high temperatures that are incredibly difficult to decarbonize.
So I guess the key question, or a key question anyway, on Sublime's process then is sort of the energy intensity of it. Obviously, we're switching from what is currently relatively cheap fossil-fueled kiln heating to electricity, which is lower emissions, but currently more expensive. So it sort of all comes down to how much energy it requires to run the process. How do you think about that?
Yeah, energy is super important, and we think of all the different ways to decarbonize cement, be it electrifying parts of the kiln or moving to post-combustion carbon capture. All of those are energy adders onto the system, and have the possibility of being cost adders as well. Since electric heating is never as efficient as direct combustion heating. So Sublime's process produces a cement that has the same embodied energy as Portland cement today. And we also have a pathway to further reducing the embodied energy as well, to making it a path to half as much embodied energy. And I think that's important because as we look over the millennia for how technologies evolve, it's usually the lowest energy, most efficient process ends up being the winner.
All right. So I guess final question, what are you seeing in terms of the market? How much demand pull is there for low carbon or zero carbon cement from major customers? And I guess who are those customers? And do you feel like it's from, the years that you've been working in this space, is it moving any faster? I was sort of notoriously a conservative, slow moving, though fast setting market.
Yes, a very stoic industry, and for good reason too. But I've seen in my 3 years at Sublime a tremendous amount of interest in low carbon cement. So a lot of interest from corporations, even from individuals. And I think what's really interesting is that, like I said before, with 90% of the cost of cement being labor and only 5% being materials costs, even as these new technologies for making cement, until they get to scale, they're going to have some sort of green premium associated with them. But that green premium ends up being budget dust at the end of the day for the building owner. So it's even, compared to HVAC or everything else you're putting into a building, it's so cheap. And it's one of the biggest levers for a company's scope 3 emissions. And so we're seeing a lot of these companies with internal prices on carbon getting really excited about low carbon cement.
All right. Well, I know we're out of time, but that's a good way to end it. Let's hope that all this demand materializes. Let's hope that all these solutions scale up and that we end up in a place where we are still perhaps producing more cement than we are basically anything else in the world, but the emissions profile goes from like 8% of global emissions to 0 by mid-century. Leah, thank you so much for finally doing this with me.
Thanks, Shayle.
Leah Ellis is the co-founder and CEO of Sublime Systems. What did you think? What did we miss? There's a lot going on in cement decarbonization world. We're always excited to hear feedback. You can find the show on Twitter at @CatalystPod. You can find me there too. If you liked it, go over as always to Spotify or Apple Podcasts or wherever you get this show and leave us a rating and review. This show is a co-production of Postscript Media and Canary Media. You can head over to canarymedia.com for links to today's topics. And as always, Postscript is supported by Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and agriculture, transportation and logistics, advanced materials and manufacturing, and advanced computing. This episode was produced by Daniel Waldorf, mixing by Greg Vilfrank and Sean Marquand, theme song by Sean Marquand. Our managing producer is Cecily Meza Martinez, and special thanks to my dog Primo for being quiet while I record this outro as he sits on my lap. I'm Shayle Kann, and this is Catalyst.